When a speaker cone pushes outward, it creates a mechanical wave traveling through the air. But that physical chain reaction of colliding molecules is completely separate from the subjective mental experience we call hearing. In the physical world, sound has no inherent pitch and no actual volume. It is strictly a series of atmospheric pressure fluctuations waiting to be decoded. This chart shows how our brains translate those objective physical measurements into a subjective reality. A frequency measured in hertz becomes the sensation of pitch. Amplitude, or sound pressure level, is perceived as loudness, and the complex shape of the waveform is translated into timbre. Getting from a chaotic wave of air molecules to a precise mental perception requires an incredibly sophisticated biological processor, and that process begins on the outside of your head. The fleshy outer ear, or pinna, acts as a directional encoder. By bouncing incoming sound waves around its specific ridges and folds, it naturally boosts frequencies around 1500 Hz, which helps us locate exactly where a sound is coming from. From there, the wave travels into the ear canal. Acoustically, this passage functions as a quarter-wave pipe, a cylindrical tube that is closed at one end by the eardrum. Because of its specific length and shape, this biological pipe naturally resonates to amplify mid-frequencies. Sound waves between 2 and 7 kHz receive an acoustic boost of up to 20 decibels. That specific amplification range perfectly matches the exact frequencies we rely on to comprehend the consonants in human speech. The outer ear effortlessly filters and boosts these crucial frequencies out of thin air. But now, that airborne wave hits the eardrum, a solid physical barrier protecting a fluid-filled chamber that, under normal circumstances, would bounce 99.9% of airborne sound right back out. This creates a major physics problem known as an impedance mismatch. Airborne sound waves simply lack the density and force required to efficiently transfer their energy into the heavy, incompressible fluid of the inner ear. To cross this barrier, the middle ear uses the malleus, incus, and stapes. These three tiny, interlocked bones act as a mechanical transformer. First, they utilize area reduction. The eardrum captures sound over 80 square millimeters, focusing all that energy into the tiny oval window. Combined with the bone's lever action, this total pressure amplification translates to roughly a 40 decibel boost. This mechanical transformation perfectly bridges the density gap, converting weak air vibrations into a concentrated physical force strong enough to push fluid. But this massive biological amplification system introduces a severe physical danger. Dangerously loud, low-frequency sounds could easily overload and destroy the delicate mechanics of the inner ear. To prevent this, the middle ear relies on the tensor tympani and stapedius muscles. They act as an automatic biological volume knob, instantly contracting when exposed to loud sounds under 1.2 kHz. This muscle contraction dynamically stiffens the entire bone chain. It physically restricts the transfer of destructive low-frequency energy, while still allowing higher frequencies to pass through safely. The middle ear operates as a dynamic gatekeeper, boosting specific frequencies necessary to cross the fluid barrier, while actively clamping down to protect the system from overwhelming lows. The newly amplified wave now pushes through the oval window, sending intense ripples of pressure directly into the fluid of the snail-shaped cochlea. Running right through the center of this fluid is the basilar membrane, the auditory system's ultimate physical frequency sorter. The membrane's narrow, stiff base vibrates violently to fast, high frequencies. By contrast, the wide, loosed apex is tuned exclusively to slow, low frequencies. Because low-frequency waves must travel over the high-frequency base to reach the apex, loud bass can easily swamp quieter treble notes. The basilar membrane physically unwinds a chaotic, tangled sound wave into its individual frequency components, mapping them cleanly across its surface. Sitting directly on this membrane are thousands of microscopic hair cells, waiting to be triggered by these localized vibrations. The outer hair cells act as active biological amplifiers. They physically change shape in real time to sharpen frequency tuning, increasing our hearing sensitivity. Meanwhile, the inner hair cells act as final biological microphones. They take sharpened mechanical vibrations and convert them into binary electrical nerve impulses. These precise electrical impulses travel up the auditory nerve to the brain's cortex, where the raw data is finally decoded and perceived. We do not passively hear the world around us.